I'm session chair for this presentation on the nuclear energy series. We're pleased to have Dr. Iurii Shybetskyi, Principal Scientist of the State Institution Radioenvironmental Center of the National Academy of Sciences of the Ukraine. We'll be hearing about radioactive waste disposal in Canada and around the globe. Want to remind everybody for one of the reasons for this, there's a need for clean, sustainable energy. Energy is the golden thread that connects economic growth and everything else. And it's really important. I'd also like to remind people of the role of IEEE, which is to ensure that a response to climate change is substantial, appropriate, and properly engages IEEE, its members, and the larger technical professions. This is from past President, IEEE President Saifer Rahman. The goal is to provide a neutral platform and to function as a technology provider. This whole series is brought to us by the IEEE Vancouver section, who has done all the heavy lifting, the IEEE Future Directions, the SUSTEC Initiative, IEEE NPSS Nuclear Plasma Science Society, and the Sanders Association. The goal is to be reaching out to a broad audience and a general community with interest in serving the needs of the profession. So here we are. You can search for it, but all the previous talks are now available on demand. And we're here today on the 2nd of July to listen to Radioactive Waste Disposal by Dr. Iurii Shybetskyi. Here you can see a link to the series page, email list, and registration. And next 2 weeks from now, on July 16th, we'll have a talk by Dr. Robert Hayes on a technical review of common myths about nuclear energy. It'll examine the various common myths on the anti-nuclear claims that appeal to fears of extreme radiological risk. It'll review the radiation risks. It'll talk about social myths, and there will be some additional data on hypothesis. For registration and more, you can see it there, and you can search. Today, we're lucky to have Dr. Iurii Shybetskyi talk. He will cover issues of radioactive waste management that arise at various stages in the nuclear fuel cycle and in the modern production of electricity and the use of nuclear energy in industry, science, and medicine. The main attention will be paid to the final solution of the problem of radioactive waste management, their safe disposal. The current state of prospects and political challenges of radioactive waste management in Canada will be considered, and around the world will be considered. Dr. Iurii Shybetskyi has over 40 years of experience, including 25 in the field of radioactive waste geological disposal. He has expertise in radioactive waste disposal, siting for geological disposal facilities, safety assessments, and development of national regulations, norms, and programs for radio waste management. He has authored over 100 publications, including 6 books, and he has participated in the development of laws in the Ukraine. And he has participated in various international projects funded by the EU. So with that, I'll pull up his charts, and we'll get started with his presentation.
Okay.
Hang on a second. Okay, Iurii, take it away.
Okay. Hello, everybody. Dear organizers of this presentation series. Thanks a lot for your invitation to participate in these events. Charles, thanks a lot for kindly introducing me. For me, it's a great honor to speak before you. Today, I would like to talk about radioactive waste disposal options for Canada and around the globe. Next slide, please. The aim of my presentation is to give you the general idea about the technical side of disposal of radioactive waste from different sources, taking into account the Canadian intentions of deployment of a small modular reactor. The essential part of my presentation will focus on geological disposal of radioactive waste and current state of the solution of this issue in Canada. To reach this aim, I'm going to speak about the topics listed on this slide. Next slide, please. First of all, I would like to emphasize that in the nearest future, nuclear energy will remain the cleanest and the safest form of energy, and it will be impossible to solve the problem of climate change and sustainable development of our civilization without its use. However, the downside of using nuclear energy is the need to handle radioactive waste. Next slide, please. Let us start with the general approaches to safe disposal of red waste. Next. Peaceful using of nuclear energy started since the 19th of the last century. Currently, approximately 400 power reactors are in operation worldwide. Their installed capacity is also close 400 gigawatts. The safe and responsible using of nuclear energy is realized by connected sequence of technologies which are joined in nuclear fuel cycle. Each part or technology of nuclear fuel cycle generates radioactive waste of different activity level. And the final aim of radioactive waste management is its environmentally safe disposal. Next. The classification of radioactive waste can be built on base of different criteria. Recommended by International Atomic Energy Agency classification uses a criterion of disposal possibility. Safe disposal is the final goal of radioactive waste management. Depending on activity and nuclide half-life, different waste classes need different disposal technologies. The most dangerous class of radioactive waste, high-level waste and spent nuclear fuel, can be disposed only in deep geological repository, which is locates in stable and predictable geological conditions. Next, please. Okay. The higher the activity of waste and the longer their danger persists, the more reliable and expensive facilities are used for their disposal, and the deeper these facilities are located. In general, very low level waste and low level waste are disposed of in the surface and near surface facilities. The share of such waste is approximately 90% of total amount of waste, but the activity is only 0.1%. Intermediate level waste and high level waste should be disposed in geological repositories, and 0.1% of HLW contains 95% of total activity of all waste. The left picture on this slide shows the list of commonly used barriers for different disposal facilities. Radioactive waste disposal facilities usually are the multi-barrier system composed of engineered and natural barriers. The safety of system is maintained even one of the barrier fails. The more dangerous the radioactive waste, the more engineered barriers are used, and the longer natural barrier must work. So the system with limited number of engineered barriers can be used for disposal of low-level waste and very low-level waste. In this case, barriers works during only several tens or 100 years. And such facilities stay under regulatory control until they are decommissioned. In case of disposal of spent nuclear fuel and high-level waste, engineered barrier systems works up to several tens thousand years, and natural barriers up to million years. In this case, engineered barriers are complementary to the natural, and after closure, such facilities provide passive safety independent from regulatory control. The right pictures demonstrate the radionuclide distribution in engineered and natural barriers designed for Canadian Deep Geological Repository concept in 1 million years. As a result of multi-barrier systems work, doses from DGR is 100,000 times below regulatory limits, and only a few radionuclides from disposed used fuel, iodanium 129, able to reach the biosphere. Next, please. Now I'm going to inform you about international approaches and experience in waste disposal. Next slide. Very low, about surface disposal of very low level waste. Such waste arise from operation and decommissioning of nuclear facility, and its activity is slightly above the level of which specified for the clearance of material from regulatory control. Other such waste containing natural occurring radionuclides may originate from mining and processing of minerals. An adequate level of safety for low-level waste may be achieved by its disposal in very simple engineered surface facilities. You can see several examples here. This is Ceres facility in France, Valputs facility in South Africa, and NPP sites facilities for disposal low-level active waste in Sweden. Another management options for some part of very low-level waste may be use it for road construction. Next, please. About near-surface disposal of low-level waste. Low-level waste requires robust containment and isolation for a limited period of time, up to a few hundred years. In many countries, it is assumed that institutional control can be relied upon for a period of up to around 300 years. Low-level waste can be disposed in near-surface facility. Appropriate design options may range from simple or more complex engineered facilities and may involve disposal at varying depths, typically from the surface down to 30 meters. Here you can see so-called CSA facility in France. Next slide, please. About disposal options for intermediate level waste. Generally, intermediate level waste contains long-lived radionuclides in quantities that needs a greater degree of containment and isolation from the biosphere than it is provided by near-surface disposal. Disposal in facilities at a depth of between few tens and a few hundred meters is indicated by International Atomic Energy for intermediate level waste. Long-term safety for disposal facilities as such intermediate depths will not depend on application of institutional control. On this slide, you can see SFR and SFL facilities in Sweden. They are located on the depths of approximately 100 meters below the Baltic Sea. And the lower pictures shows the approach of Finland to co-disposal of low-level waste and intermediate-level waste. Next, please. There are several repositories for radioactive waste in the world, which can be considered like deep geological repositories. However, only non-heat generating waste are disposed here. Here are examples using former mines for the disposal of low and intermediate level waste. Practical disposal of waste was carried out in Germany in the mines Asse and Morsleben. In the mine Asse, after the placement of waste, an influx of underground brines was recorded. Therefore, a decision was made about retrieval and redisposal of this waste. Another example of such disposal is the Conrad repository in Germany. It is being built at a depth of 900 meters in a former iron mine. The repository is intended for the disposal of all non-heat emitting radioactive waste in Germany. Next, please. Waste isolation pilot project in the USA is a practical example of a repository for geological disposal of intermediate level waste. More precisely, for transuranium waste from the military industry. It was created in bedded salts at a depth of 650 meters and has been in operation since 1999. Here I would like to say about advantages of different geological media which can be used for geological disposal of radioactive waste. The advantages of geological disposal in salts are no water flow, self-healing of cracks in salts, plasticity of salts which encapsulate waste drum, high thermal conductivity, ease of mining, and stability of geological condition over a long period of time. Next, please. High-level waste, spent nuclear fuel, or vitrified high-level waste is the waste that contains large concentration of both short and long-lived radionuclides. High-level waste needs a maximal degree of containment and isolation from the accessible environment to ensure their long-term safety. Such containment and isolation is usually provided by the integrity and stability of deep geological disposal with full system of engineered barriers. High-level waste generates significant quantities of heat from radioactive decay and normally continues to generate heat for several centuries. This is an example for the future deep geological repository for spent nuclear fuel that is planned to be built in Sweden in 2032. For deep geological repository, the deep geological repository will be placed in crystalline rocks, more precise in granites, at a depth of approximately 500 meters. The advantages of this type of host rock are mechanical stability of mining openings, stability and predictability of geological condition of the site for a long period of time. A future of Swedish concept, KBS3 concept, is the use of a thick-walled copper container. Such container will completely contain radionuclides for 100,000 of years. However, it is very expensive due to use a lot of copper. Next slide, please. This is example of deep geological repository which will be built in argillite, in clay rocks. In France, it is planned to locate DGR in such rocks at a depth of 500 meters. High-level waste, a product of spent nuclear fuel reprocessing, will be disposed here. The advantages of this type of rock are absence of crack and fractures, very slow water exchange, and high sorption properties. Next, please. A very promising concept for disposal of high-level waste is so-called deep borehole disposal concept. It involves the placement of waste in a large diameter of boreholes up to 1 meter at depths of 5 to 5 kilometers in condition of very stagnant groundwater regime. In comparison to mined deep geological repository on the depths of 600 meters, this concept is potentially safer, less reliance on engineered barriers, and secure, greater cost effective, earlier in implementation, easier siting, and has a low environmental impact in space and time. Deep borehole disposal concept can be very promising option for disposal of all inventory of small modular reactor waste directly on a reactor site. Next, please. To finish this part of presentation, I'd like to say next. As you can see on this picture, most of the countries with developed nuclear power, 25 out of 35, implement disposal program for spent nuclear fuel and high-level waste. These programs are at different stages. Some of the countries are close to commissioning deep geological repository. Some are actively working on site selection. Some have decided on type of host rock or disposal concept. And some countries wait and see. Finland, Sweden, and France are closest to building deep geological repository. Next, please. Now about waste inventory and Canada and planned disposal option. Next, please. Nuclear power plants have been producing electricity commercially in Canada since the early 16th. Today, 5 plants in 3 provinces house 22 reactors, power reactors. Nuclear energy produces about 15% of Canada's electricity. All nuclear power reactors in Canada are CANDU type, Canadian deuterium uranium reactors. These are pressurized heavy water reactor, and they use natural uranium as fuel and heavy water as a coolant and moderator. Next, please. This slide provides data on material composition of radioactive waste of different activity categories for different part of nuclear fuel cycle in Canada. Here, these waste are grouped according to technologies for reducing their initial volumes for future disposal. Reducing waste volumes is aimed at reducing the cost for their disposal. Waste processing method vary based on the physical properties of waste and can include mechanical volume reduction, cutting, segmentation, compaction, incineration, metal melting, decontamination, etc. For example, when incineration, the volume of waste is reduced by 100 times, and when compacted by 8 times. Next, please. On this slide, you can see estimates of amount of waste in Canada that will need to be disposed of in various repositories. The estimates are made taking into account the design operation time of the existing reactor fleet. In particular, 5.5 million fuel bundles, 32,000 cubic meters of intermediate level waste, and 3.4 million cubic meters of low level waste will be accumulated in Canada by the end of this century. Next slide, please. The main used fuel storage site in Canada are shown here, and the waste will be stored there until disposal facilities are created. As we can see, 90% of volumes are in the province of Ontario. This is the answer to the question why the province Ontario was chosen to host the geological repository. Next, please. In Canada, the integrated strategy for radioactive waste management was approved in 2023. This strategy defines disposal option for different categories of waste. And the companies that are responsible for development of appropriate repositories. There is no disposal plan in the Canadian strategy. It was mentioned in strategy that there is not no disposal plan for 10 cubic meters of high-level waste, 51 cubic meter of intermediate level waste, and approximately 300,000 meters of low-level waste. Next, please. This slide visualizes the integrated strategy for radioactive waste management in Canada. It should be noted that rad waste in Canada are divided in 4 broad categories, and the classification of radioactive waste which is used in Canada is very similar to recommended by IAEA. Only one difference. IAEA divided 2 classes, low-level waste and intermediate level, and very low-level waste. And this waste in Canada are included in one category. It was shown in previous part of the presentation that disposal concept for all categories waste have been developed and partially implemented in practice around the world. Canada also developing the necessary disposal concept, and the question is how effectively use them in practice. For example, I would like to note that separate disposal of low-level waste and intermediate level waste within separate repositories can allow to reduce disposal cost by factor 4.5, and the same can be reached at separate disposal of low-level waste and very low-level waste. Next, please. Now several slides about disposal concepts which are developing in Canada. This is an example of a Canadian concept for disposal of low-level waste, so-called near-surface disposal facility for low-level waste. The facility is expected to be operational for approximately 50 years. This facility can besides to hold 1 million cubic meter of radioactive waste, and the waste to be disposed here includes the following: the waste now in storage that has resulted from legacy Canadian nuclear laboratory operational and decommissioning activities, the waste to be generated from decommissioning of existing CNL building, and future waste arising from continuing CNL activities. Another example of technology for disposal of low-level waste originated from mining activities is so-called long-term waste management facility, which is located in municipality of Port Hope. It has capacity of approximately 2 million cubic meters. Both these repositories are an above-ground engineered containment mound with a low permeability-based liner and final cover. It should be noted that the concepts of NSDF and LTWMF are suitable rather for disposal of very low-level waste. Next, please. Very interesting repository was designed in early 2000s for co-disposal of low-level waste and intermediate level waste, originated from operation of OPG's NPP. It looks like a typical, very safe, deep geological repository with full system of engineered barriers. However, this project was stopped due to social reasons. It was not accepted by local community of First Nation. It should be stressed classes. The repository must be designed for the highest class of waste to be disposed of in it. And of course, it increased cost for the lower class of waste. Next, please. On this slide, you can see the key components of Canadian deep geological repository concept. It includes like typical multi-barrier concept, waste form, engineered barrier system, container, buffer, and sealing materials, and host rock. It would be noted here two revolutionary moments or know-how of the Canadian concept, which significantly reduce the cost of waste disposal and simplify the process of installing the containers in the placement rooms. The first is the use of copper-coated container instead of an all-copper container, like in Sweden concept. And the second is the use of a bentonite box instead of bentonite rings around containers. Next, please. It will be the next part of my presentation, and here I will talk about the state of the art of Canadian DGR program. Next, please. The research work on Canadian geological disposal program began in 1978. They were carried out by company IECL. A large amount of research has been carried out in the Whiteshell underground laboratory. In 2002, the Nuclear Waste Management Organization company was established. The company has developed a plan for deep geological repository development and a special approach for this called adaptive waste management. Since 2010, the process of site selection has begun. Next, please. In the process of screening, 22 site options were identified, and in 2024, 2 sites remained for the future consideration: South Bruce and Ignace, both in Ontario province. Next, please. On the South Bruce site, the host rock is sedimentary rock, similar to a French site, and on the Ignace site, Archean granitoids of review batholith, very similar to Swedish site. NWMO is confident that a deep geological repository could be constructed at both sites in a manner that would provide safe long-term management for Canada's used nuclear fuel. And recently, at the end of November 2024, NWMO selected Ignace site for deep geological repository and will continue to investigate only this site. Next, please. This slide shows NWMO's immediate plans to create geological repository. It is expected that the repository will be constructed from 2033 and commissioned in 2040-45. After that, repository will be in operation for 40 years, and after that, it will be monitored during 70 years. Next, please. And this is the last part of my presentation. In this part, I will talk about the management of radioactive waste from small modular reactor. Next, please. A small modular reactor is a source of safe, clean, and affordable energy, opening opportunities for a resilient, low-carbon future and capturing benefits for Canada and Canadians. Canada is implementing a roadmap for the deployment of several types of small modular reactor by early 2030s. You can see this type of small modular reactor. And recently, in April of 2025, Canadian Nuclear Safety Commission issued a license for construction of BWRX type of small modular reactor at Darlington site. Next, please. About safe management of small modular reactor waste. To assess the needs and possible difficulties of waste management, it is necessary to answer the question: what will be the possible waste streams from small modular reactors, and what are their difference from the same waste streams from CANDU reactors? Is it possible to use adaptive waste management concept available in Canada for disposal of small modular reactor fuel or no? Which type of repositories can be used for disposal of the intermediate and low-level waste of SMR? To solve these issues, it is necessary to determine the properties of waste stream, which is important for decision making. Generally, such properties depend on the type of fuel, its enrichment, the chemical composition of fuel and coolant, decay heat, nuclide composition, etc. Next, please. Here are the important characteristics of few of different SMRs. Their primarily analysis shows that in order to dispose of high-level waste from SMR, it will be necessary to make changes to existing adaptive waste management project. To do this, it will be necessary to carry out a large amount of research and development and develop special safety justification or develop special safety case for this fuel. Next, please. During the operation and the commissioning of SMR, both conventional and unique streams of intermediate level waste and low level waste will arise. These streams are shown on this slide. In accordance with the integrated waste management strategy, centralized disposal of intermediate level waste is planned under the responsibility of NWMO. It will also be necessary to decide how to effectively dispose LLW and very low-level waste in centralized or in multiple repositories at each SMR sites. Next, please. I would skip this slide because I will repeat it in the conclusions. General conclusion. Next slide. According to global situation, the world has accumulated significant experience both in the practical disposal of very low-level waste and partially intermediate level waste, as well as in designing and construction of repositories for intermediate level waste, spent nuclear fuel, and high-level waste. Safe disposal concepts have been developed for all waste classes. Safe disposal of radioactive waste is ensured by multi-barrier disposal system. Different strategies for disposal of different classes of radioactive waste are being implemented in the world. Usually, very low and low-level waste are disposed in the surface and near-surface repositories. Extensive practical experience has been accumulated here. There are examples of using intermediate depth repositories for co-disposal of low-level waste and very low and intermediate low-level waste. This can be specially built repositories or converted former mines. Some countries are planning to build separate repositories for intermediate level waste and separate repositories for spent nuclear fuel and high level waste. Some countries are planning co-disposal of high level waste and intermediate level waste in deep geological repository. Next, please. Canadian situation. Canada implements the integrated strategy of radioactive waste management, which covers all waste stream. Canada has experience in development of concepts for the disposal of all possible waste streams. And in Canada, it can be used also international experience. Next, please. Connected SMR waste. Small modular reactor waste streams have specific characteristics which should be considered when developing a strategy for their safe management. An extensive research and development program is absolutely necessary. To optimize the small modular reactor waste management strategy, certain organizational efforts will be needed. It should be found consensus between stakeholders between government and nuclear generating company to decide what is better, to develop centralized facilities for low-level waste, or waste owners should create their own repositories. Maybe it should be useful to decide to create maybe a new waste management organization for disposal of low-level waste, or expand the responsibility for NWMO. And it also should be decided what is better, co-disposal, low-level waste and very low-level waste, or separate. Next, please. And to finish my presentation, I would read one very interesting quotation. There are a number of issues for implementing of integrated waste management system in Canada, such as some waste may need to be recharacterized and reclassified under the unique classification, but this may be expensive for some waste owners. If co-disposal is being considered, the repository must be designed for the highest waste class to be disposed of in it. This may increase the cost for lower classes of waste. However, the combined facility may save on infrastructure cost. Transportation of waste to be centralized facility may be a limiting factor. In Canada, the distance between sites where is waste are currently stored is quite large, up to 3,000 kilometers. However, these issues are insurmountable. Thank you very much for your attention, and I'd like to say that disposal of radioactive waste, it is not technical, not technological question. It is rather political and social question. And you can see some references which can be used for getting additional information. Thanks a lot for your attention.
Iurii, spasiba dla очень интересной презентации. Thank you for a very interesting presentation.
You're welcome.
I see a number of questions in the Q&A, so I'll start reading some of them. Are there any studies carried out on the effect of climate change on radioactive containment systems?
Yes, usually such type of studies are included in safety case development, in safety analysis report. Usually people investigate the influence of ice time, influence of global warming, and all of these events should not provide additional doses for population.
Okay. Another question, maybe somebody's from California. What about earthquakes on the underground waste disposal?
Usually the deeper disposal is, the small influence or earthquake will be for this repository. Another example, Japan is very seismic dangerous country, but they design repository without damage from seismic activity. Seismic activity can be dangerous when repository is in operation. After closure, it's not very very important event.
Okay. Another question that always comes up is how to access the video on demand. So I pasted a link into the chat. Otherwise, if you just search for the Future Directions Nuclear Presentation Series, You'll eventually get there. There is a question about the very diverse set of configurations for storage and containment. Can you please discuss the current practices and requirements for sensors used in monitoring the radiation levels? It must not be practical to monitor within a container or borehole, but where would you place the sensors?
Excuse me, I missed.
Okay,
Could you repeat? Too long for my small English knowledges.
sure. Let me simplify it. What
Yeah,
sort
yeah,
of
please.
monitoring will be required for these sites, and where should the sensors be placed?
Mhm, mhm. As far as I know, usually people designed monitoring system for repository, but it is very important for operational period of repository. Why? Because it can provide additional information for modification of design. After closure of repository, it not maybe so important because there is a question what we should do if we will detect the leaching of radiation. Uh, um, and some designs uh, some designs uh, include retrievability of waste. In this case, it will be very monitoring. It will be very helpful. But I can repeat only that after closure of repository, monitoring can provide information only for social media to demonstrate that everything is fine with our
Yeah, that makes
containers.
sense. In the United States, a lot of waste stays at the reactors because in the US, we're waiting to implement storage facilities. Is that common outside of the US?
Uh, For example, in Ukraine, yes, we also have the same situation. Uh, I know that in the United States there are. It was very interesting project, Yucca Mountain, and it also was stopped due to political reasons. I guess that taking into account the high level of technological development of the United States, and due to very proficient people which work in this sphere, it can be this problem can be solved in very short period of time. Uh, for this, it is necessary only political view, only political view. Mhm.
Okay. Another question is, do you think repurification, recycling technologies can be implemented and will reduce the amount of waste?
Uh, you mean reclassification, or?
No. If I understand it right, a rod will be at 99.9% purity, and when it gets down to 95% purity, it needs to be put out of service. If one were to recycle, repurify it to bring it up to 99.9%. Um,
Mhm.
so is that something you think will be feasible, or do you think it's got problems?
Mhm. That is very interesting and sophistical question. Why? Uh, for example, after reprocessing, the waste after reprocessing have very unpleasant characteristic. Usually it contains a lot of long-lived and long-lived radionuclide, which has which are very mobile. And after reprocessing, some waste should be uh, cooled a long period of time. I guess each country should decide itself what is better for this country. For example, I know that several European countries stopped the program of reprocessing. I mean the Sweden, Switzerland, Germany, but some country like France continue to do this. It is very difficult question, but in the future, and for example, some small modular reactor is designed for very interesting reprocessing project, but maybe we should wait and see what happened in the nearest future.
Okay. There's a long question. Near Chalk River, Ontario, Canada, there is a plan to build a storage site for low-level waste from
Mhm.
nearby AECL laboratories. Since the distance from the um, Ottawa River is only a kilometer, there is
Mhm.
significant opposition from residents and from downwards direction, i.e., Ottawa, Gatineau, and further down, I assume down the river. How important is the distance from the waste disposal sites to the river water, lake, or ocean? Um, and I think the issue is, does a deeply, um, if a storage facility is very deep, does it matter how close it is to a river?
Uh, yes. General answer is yes. It is very important. However, as far as I know, uh, uh, in this type of facility used multi-layer liner, multi-layer cover and multi-layer top. And these layers contains very anti-filtration protective layer. And I guess that due to using of these liners, very small quantity of water will be gain into inside of repository. So only very limited quantity of radionuclides have possibility to escape from this repository. And I guess this repository can be safe can be safe. But general answer yes. It is distance between repository and between and river is very important. The same for deep geological repository. But in this case, in case of repository, it is very important how actively is water exchange between deeper uh, underground water and surface water. In this case, deep borehole concept looks like very safe because water can be stay on the place of radioactive waste in maybe million and even billion years.
Right. Okay. In your fourth conclusion, you said there are a number of issues for implementing an integrated waste management system in Canada. Do you believe these problems can be overcome, or do you believe they will be impossible to overcome?
From technological point of view, it's very easy to overcome. The main question is political and social questions
Okay.
because it is also very good potential for reducing of cost.
So I'll talk with you offline. The issue is the word insurmountable. was used. So I'll talk with you offline about that. Okay. Um, then there's another thing. Why are we not considering the high Arctic islands as a disposal site? Few people live there, few ever will. However, there are some mines up there. With global warming in the region, it might become more accessible. Um, let's see. So, do you think a remote location in the very
I will
cold areas of Canada would be a good place?
I guess there is two sides of this problem. One problem, uh, we don't we have very limited information about water circulation under permanent permafrost.
That's
One,
a good point.
one, one, and another question. Uh, there are no very extended experience around the world in development of safety case for this type of geological situation. But I know this this proposal to locate repository on the north, but it requires such a kind of decision requires a lot of research and development work. But why not? Why not?
Okay. Um, there was another question about continuing education credits. When you fill out your um, uh, what feedback note, you can talk about it there or drop me a note if you think that's very good. Um, doing CE credits is pretty easy to do, but when only one or two people collect them, for a volunteer, it's a waste of time and very frustrating.
Mhm.
So if you think it's really good, drop us a note. I put my name into the chat box. Ahmed, do you have any questions or comments? Is Ahmed still on? Maybe not. Okay. Micah, do you have any questions or comments?
Well, thank you very much, Yuri. It was great listening to you again. I truly appreciate the big amount of work that went into this presentation. It's a tremendous amount of information. One of the questions that's been arising is if we store the spent fuel properly, which we need to do, will it be accessible in the future for reprocessing if we ever desire to do so? In other words, can we open the vaults again and get at the spent fuel rather than mining more uranium?
Uh, as far as I know, two cycles of interim storage of spent nuclear fuel, the cost for two cycles, I mean for 200 years, will be the same like disposal. So it is maybe economical question and question of technology.
Yeah,
Okay.
yes, of course, economics comes into it, right? Always. Um, So here's another question that I see in the chat, and I don't think we have seen that yet, is what are the future developments expected in nuclear reactor waste disposal? And what is the projected volume?
Well, the projected volume was actually in the charts, so people
Yeah,
can review that
right.
there. Um, but
Uh,
Yuri, go on.
Are there any other developments expected? That was the question here.
Maybe concerning disposal of radioactive waste, last time it was very people very interested in borehole disposal. Why? Because it is cheaper, faster, and safer. There is, of course, technological problem because there are not commercially available technology for drilling of for deep drilling with a very large diameter. But maybe in several years or 10 years, we will get such technologies. And now people think about classical, and people are developing classical type of deep geological repository.
Yeah, and some people were talking about shooting the spent fuel into space too, right?
It's also a very interesting question. For example, usually the limit of risk for irradiation of people due to disposal of waste is 10 minus 6 per year. But the possibility of accident with spacecraft is only 10 in power minus 3. It means that it is very dangerous, especially taking into account the possibility of very extensive contamination. But when we will have spacecraft with risk on the level of 10 minus 7, it will be very nice option. Extremely ecologically friendly option.
Very, very good. So right now we have a 10,000 factor of risk to look at. Yes. There was one question is whether people are actually looking at the safety radiation dose levels, whether there are changes to be expected. This is a little bit outside this talk maybe, so I'm kind of wondering.
Yes, for me it's pretty difficult question, but as far as I know, usually the dose limit for geological disposal is 10 microsieverts per year for people during all period of potential dangerous, during at least 1 million year.
Yeah. There's one question that just ended up in the chat box, and disposing of nuclear waste in the ocean is something to always be researched. But I'll point out that in the 1940s, off of Southern California, people thought it would be fine to dispose of what do you call it? A poison, an insect poison that I'm forgetting the name of right now. And they put it out to sea about 5 miles. Well, it turns out almost all fish in the waters of California, Southern California, have unacceptably high levels of that chemical. So it has to be researched carefully. Putting something in the Marianas Trench might work, but it could do very difficult things.
I think I have exhausted my questions at this end.
Okay.
Okay.
Well, Iurii, I want to thank you for an interesting talk. And that'll be it. We'll post the video as soon as possible. And if you get a survey, please answer it. Thank you.
Yes, and in the survey you have,
One more time.
you have an opportunity to give feedback, and if there's some concerns, please list them there, and we can get back to you. That's a very good way to get in touch with us. So thank you very much.
One more time, thank you very much for possibility to speak in front of you. Thank you very much.
Well, thank you very much, Iurii. It was great. And with that, goodbye to everybody.
Bye-bye.